So we've just seen how polynomial degree can be used to lower bound quantum query complexity. Now let's see how we can actually apply this polynomial method. And we're going to look at the case of applying it to the OR function. Okay. So in general, it's not so easy to lower bound approximate polynomial degree. But the OR function is very nice because it's an example of what's called a symmetric function. And what that means is that f of x only depends on the number of ones in x. Okay, so a function is symmetric, a function f is symmetric if f of x only depends on the number of ones in x and not the location of those ones. Okay, and that's certainly the case of the OR function. In the case of symmetric functions, we actually completely understand the approximate polynomial degree. So we have a characterization of the approximate polynomial degree of any symmetric function. And today I'm going to tell you a little bit about how that works, at least how the lower bound works. Okay, so let's say we have a function f on n-bit strings and that it's a symmetric function. And let's say that p is an epsilon error approximating polynomial for f, and that p has degree d. Okay, and now what we're going to do is we're going to symmetrize p. Okay, so what that means is that we are going to create a new polynomial, p sim, by summing the original polynomial over all possible permutations of the input variables. Okay, and then we normalize by 1 over n factorial. Okay, so notice that this symmetrization process, if I were to do this to f, then f is completely unchanged by this process, right? And that's exactly because since f is symmetric, f of x is always going to be equal to f of pi of x for any permutation pi. Okay, and now, although f is symmetric, p doesn't necessarily have to be. Okay, all we know is that for every x, it's at most epsilon away from f of x, but it doesn't actually have to be symmetric. But what we do by the symmetrization process is we create a symmetric polynomial. Okay, so by this construction, p sim is going to be a symmetric polynomial, and moreover, it will still be an epsilon error approximating polynomial for f. Okay, so let's see how this works on an example here. Okay, so again, let's just think about the 2-bit AND function, and I've kind of artificially constructed a polynomial here, which is not symmetric, but that approximates the AND function. Okay, so it's just 6 over 20 times x1 plus 7 over 20 times x2. Okay, so it's always at least at most 7 over 20 away from the value of f of x, but it's not actually symmetric, right? Because it has a different value on input 0, 1 from its value on input 1, 0. Okay, so in this case, p sim is just going to be the average of two polynomials, p itself, and where we switch the input variables x1 and x2. Okay, so p evaluated at x2, x1. Okay, so when we compute what this is, given our definition of p, this is just going to be 13 over 40 times x1 plus x2. So now we have a symmetric polynomial, and it's still a 7 over 20 approximation to f. And actually the error on each Hamming weight is just going to be the average of the previous errors. Okay, so on say input 1, 0, initially p had error 7 over 20, but now p sim on input 1, 0, its error is going to be 13 over 40, right? Which is the average of the error that the original P had on inputs of Hamming weight 1. Okay, so this is going to be the key trick, the first key trick for us to lower bound the approximate degree of the OR function. And this trick goes back to Minsky and Papert in their book about perceptrons, the symmetrization technique. Okay, so let's dig in a little bit more about what PSym looks like. Okay, so again, PSym, it's a symmetric polynomial. So that means that the coefficient of a monomial only depends on the degree of that monomial. Okay, not which variables are actually present in that monomial. Okay, so that actually means that P is described by just d+1 many numbers. So they're numbers C0 through CD, where basically Ci is the coefficient of every monomial of degree I. Okay, so we can write PSym in the following way. So it's, our original P was degree D. So PSym we can write it as a sum from k equals 0 to d of this coefficient ck, and that coefficient is going to multiply every single monomial of degree k. Okay, so PSym has a particularly simple form here, and it's just described by d+1 many numbers. Okay, so here's our symmetric polynomial, and now we're going to try to simplify it even further. Okay, so focus on this term here, right? So the sum over all subsets S of size k of the monomial, which is just the product of the variables in S. Okay, and let's just look at an example. So let's say that X has Hamming weight 4, okay, and the 4 ones are at the beginning of X. And let's say that we're looking at subsets of size 2. So which monomials of degree 2, when evaluated on this X, actually evaluate to 1? Okay, so that's going to be the case if S is a subset of the locations where X is 1, right? So if S is a subset of 1, 2, 3, 4. Okay, so these are all the sets of size 2 that are subsets of 1, 2, 3, 4. In particular, the number of such sets is just 4 choose 2. Okay. So this term here is just going to evaluate on, for this particular X to 4 choose 2. Okay, and that's going to be true for any X of Hamming weight 4. Okay. So in general, you can show that this term here is just going to be equal to the Hamming weight of X choose K, right? Because that's exactly how many subsets of size K there are, such that this monomial will evaluate to 1 on X. It's exactly the number of subsets S of size K which are actually contained in the set of ones in X, right? And those are the monomials which are going to evaluate to 1 here. Okay, so we can use that to further simplify our polynomial PSym. Okay, so now PSym looks as follows, right? Just a sum over k from 0 to d, ck times this binomial coefficient. Okay, and you see here that this expression only depends on the Hamming weight of X. Okay, so what we're actually going to do now is to define a univariate polynomial, P of z, such that P of the Hamming weight of X is actually equal to PSym of X. So we can see how to define this univariate polynomial, right? So P of z is just going to be the sum from k equals 0 to d, ck times z choose k, right? And I've just written out z choose k here so that, to make it obvious that this is a polynomial in Z. The largest value of k here is going to be D, so this term here is always going to have degree at most D. Okay, so in particular, I mean, the degree of this term is k, and k is always at most D. Okay, so now we have a univariate polynomial of degree at most D with the property that this univariate polynomial evaluated at the Hamming weight of x is actually equal to p sim of x. Okay, and this is a very, very powerful trick, right? Because now it suffices for us to just show lower bounds on the degree of a univariate polynomial. And univariate polynomials are much more familiar to us, and they're much easier to reason about. Okay, so now I'm going to look at this symmetrized picture for the AND function. Okay, so let's say that n equals 10, right? So originally we're talking about the AND function on 10-bit strings, but now I've moved to this symmetrized picture. Okay, so you should think of 0, 1, 2, 3 here as representing the number of ones in the input. Okay, and for our symmetrized polynomial here, we know that for every integer point from 0 to 9, it must be in the region minus 1/3, 1/3, right? I mean, given that it's a 1/3 approximating polynomial for the AND function. On the other hand, on input 10 here, it has to be at least 2/3, okay? Because the AND function evaluates to 1 on an input of Hamming weight 10. Okay, so what this means is that this polynomial is kind of bounded in this whole region, at least on the integer points. So on all the integer points in this region, we know that it has to be in this little window here between 1/3 and minus 1/3. Okay, on the other hand, on input 10, it has to jump out of this window, right? And it has to be, at least 2/3. Okay. And there's a nice theorem that tells us that this is actually hard for a low degree polynomial to do. Okay, it's hard for a low degree polynomial to be bounded in this big region, at least on integer points, and then quickly jump to a larger value here. Okay, so more precisely, we can use a theorem of Markov. So this is a theorem of Andrei Markov, who showed the following. Okay, so basically what's going on here is it says that the derivative of a polynomial, the maximum derivative in the interval from 0 to n, is at most the degree of the polynomial squared divided by the length of this interval, n, okay, times the maximum absolute value of the polynomial in this interval. Okay, so this is like what I was saying, but there's not the restriction to just consider integral points. Okay, so this is basically saying if you're completely bounded in a small window here and you have low degree, right, then your derivative cannot be too large, right? So it's giving you an upper bound on the derivative in terms of your degree and how bounded you are on this interval. Okay. So we can apply this to our case for showing a lower bound on the approximate polynomial degree of the AND function, but we have to do a little bit of case analysis because we don't know that our polynomial is completely bounded in this interval. All we know is that it's bounded on the integer points in this interval. Okay, so because of that, we have to do a little bit of case analysis, but the key thing is this theorem, and that will essentially give us what we want. Okay, so let's first think about the derivative of our approximating polynomial. Okay, so we know that at the point n minus 1, the polynomial is going to be at most 1/3, right? Because f, the n function on an input of Hamming weight n minus 1 evaluates to 0. And then we know that p of n has to be at least 2/3 because the n function on the all 1 input evaluates to 1. Okay, so that tells us that the derivative of our approximating polynomial has to be at least 1/3. Okay, so we basically have a lower bound on the left-hand side here. Okay, and we're going to use that to show that the degree must be large. So let's consider first the simple case where it actually is the case that our polynomial is bounded within this whole window here. Okay, so it never jumps out of this box, say between 2 and minus 2. Okay, so in that case, we just plug in 2 here for this max value. And we know that the left-hand side is at least 1/3. So that tells us that the degree of p squared divided by n has to be at least 1/6. Okay, so in other words, the degree of p has to be at least square root of n divided by 6. Okay, so that's kind of the first case where we assume our polynomial is just fully bounded in the interval, and then we can just directly apply this result. Okay, now let's consider the second case, that maybe the polynomial somewhere, it jumps out of this window. So suppose that the maximum value of the absolute value of p on the interval between 0 and n is actually h, which is bigger than 2. So in this case, we can actually get a better lower bound on the derivative of p. Okay, and why is that? So if we know that somewhere in this window between 0 to n, it takes on value, absolute value h, right? So it jumps out of this kind of box here, this 1/3 minus 1/3 box. But we know that there's going to be an adjacent integral point where the polynomial has to get back down to a value inside the box, right, between 1/3 and minus 1/3. Okay, so that tells us that the derivative of p actually has to be at least h minus 1/3. Okay, so now if we plug in h here, and this side will be at least h minus 1/3. Okay, and if you just do a little bit of algebra here, you find out that in this case, the degree of p has to be at least the square root of 5n over 6. Okay, so the main point is that either way, the degree of p has to be at least a constant times root n. Okay, so now we have our lower bound on the approximate degree of the and function. Okay, so of course we started out talking about the or function, not the and function, but the lower bound that we gave, it also directly applies to the or function because there's this simple relationship between or and that preserves polynomial degree. Okay, so this actually shows that Grover's algorithm is optimal, right? Any quantum query algorithm that computes the or function on n variables must make at least a constant times square root of n many queries. Okay, so that's an example of how you can apply the polynomial method. Let me back up and just give a higher level overview of the polynomial method. So it's known that the polynomial method does not show a tight lower bound for every function. And you see that in our proof that the approximate polynomial degree lower bounded quantum query complexity, we didn't actually use the fact that the operations that we did in between queries were unitaries. Okay, so the same exact proof would work if you allowed any linear transformation in between queries. Okay, so that's kind of some intuition why we actually don't shouldn't expect this method to always give a tight lower bound. But I should mention that recently there has been a strengthening of the polynomial method that does take into account the unitarity of operations in the algorithm, and this is actually used to give a characterization of quantum query complexity in terms of a certain kind of polynomial degree.